signature sheet. We'll all sign in. Keep the sheet moving, sign it and hand it on. Everybody get a book of notes from the back? Yeah, doing it. Okay, so welcome everybody. This is the first lecture in Mathematics Fundamentals. My name is Killian O'Brien. You've got my contact details on the sheet you got at induction. So I'm in Office E115, in the John Dalton building, and that's got my email and my phone number on it and everything. So before we get started with any mathematics, we'll just do a very quick trip through the unit. So we'll switch to Moodle. I'll just show you some basic things in Moodle and just give you a quick introduction to how the unit is going to run. Okay. So we go to Moodle. This is the Moodle area for the unit. And there's information about the unit link up here. So probably many of you have looked at this already. So this gives you the basic information about what's going on with the unit. Okay. So the topics covered in the unit are listed there. I'm going to start today with looking at convergence of sequences of series. We go through set theory, logic, an introduction to group theory, very small introduction to group theory. We cover complex numbers, some basic stuff about functions, and then calculus. So calculus occupies most of the second term, doing differentiation and integration and doing a rigorous treatment of that. Just want to pick up a book from the back desk. Is there any left there? Yeah, there's loads more over there. Okay. So the teaching staff are myself and Saeed Abuzur. And then there's 3 tutorial groups. So everybody goes to 3 lectures every week. I was going to do some of these books over the other side. Hi there, come on in. Just grab a book of notes there. Come in. So the 3 lectures every week are split between myself and Saeed. My topics are on the left there, sequences, series, and so on. Saeed's going to go through set theory, logic, and so on. I'll leave him to introduce his material when you see him. And the teaching pattern is, this is my lecture every week. Just get a book as you come in there. This is my lecture every week. The first lecture, and there's 2 lectures on Thursdays. One of those is Saeed's every week. The third lecture alternates between the 2 of us, back and forwards. I take it one week, he takes it the other week, and so on. Then everybody's going to one tutorial taken by one of the 3 tutors, which is Saeed, Dr. Kowalczyk, and Dr. Bierbauer. Doctor. So how's the unit assessed? It's very important. So the unit is assessed. Just pick up a book of notes at the back there as you come in. Yourself, yeah, the notes on the back desk. The unit is assessed by coursework, in quotes, and an end-of-year exam. Now, what does the coursework consist of? It consists of 2 in-class tests. So 2 tests that we'll host in the lectures or tutorials. Okay? The first of those takes place towards the end of term 1, and the second one takes place towards the middle of term 2. The precise dates are shown on your assessment timetable. I won't say much more about the in-class tests at the moment. They carry 40% of the mark for the unit, but we'll give you plenty of information about them as we get nearer. Okay? Plenty of support and practice papers and so on. Just get a book of notes in the back as you come in there. Yeah. And then the end-of-year exam in May is 60% of the unit. Okay? So it's a 3-hour exam covering the whole unit. Okay? You can already on Moodle, you can see some past papers from the last few years, but again, we'll talk much more about exams as we go through the unit. There's a bunch of, as well as the printed notes, so the printed lecture notes are kind of a summary of the material we're going to go through. I will do extra handwritten stuff in the lectures as well, though, so do be prepared to take notes as well, just handwritten notes. But there's a bunch of extra resources here. you can make use of. Particularly good ones are the first one, Schaum's Outline of Calculus. And this book, the second one there, Modern Engineering Mathematics, is quite good as well. Now, both of those are available as online books through the library website. Go back to the main Moodle page. They've got physical copies in the library as well. In the library block here on the right-hand side, you've got essential reading and further reading. If you click through there, that calculus is the Schaum's Outline of Calculus one, and there's this one, Modern Engineering Mathematics one, is one I particularly recommend. When you click through on those particular ones, takes you to the library website, and there's online ebook available of those, but also hard copies in the library as well. Okay. That's the rough outline of arrangements. Any quick questions just about kind of the system or the arrangements? I mean, you probably want to find out. Just get a book of notes on your way in there at the back. Hello. Just grab a book there. Thank you. I'm sure you're dead curious about the in-class tests and exam and so on, but we'll discuss those in more detail as we go through. Everybody clear on the teaching pattern? 3 lectures per week and 1 tutorial. Yeah. Yeah. Question.
Will there be any homework?
Will there be any homework? Well, in short, the answer is yes. So in your tutorial, there are tutorial questions spread throughout the book, kind of end of chapter exercises. But you're expected to work on those in your own time and to come to the tutorials, ready to ask questions, ready to seek extra help from the tutor and so on. We don't collect in regular weekly work and mark it and return it. So it's a lighter touch than the phrase homework might suggest. But no, we do. I mean, there's a general rule with university. Well, as a rule of thumb, we like to say that as a good standard, as a minimum standard, students should be doing 1 hour of self-study to match every hour of in-class session. So if you've got 16 hours a week on your timetables, as a rough guide, as a kind of base level, should be doing 16 hours of self-study per week as well. And in that, you can be going over the material from the lectures, consolidating the material from the lectures, looking over the things you didn't understand, you didn't quite get from the lectures, working on the tutorial exercises, preparing yourselves for the tutorial. To get the most out of the tutorial, you want to hit your tutor with very searching questions and help them help you clear up misunderstandings and get good experience with the topics. Okay, so let's get into it. So the first, quite a lot of my lectures in this first term are going to be talking about the issue of convergence. Now, what's on the slides here? Don't worry too much about. I mean, I don't want to stop you making notes, but what is on the slides here is more or less taken from the notes. And these slides are already available on the So don't worry about taking down all this information. It's printed in the notes. So what is convergence and divergence? Just pick up a book of notes on the back on your way in there. Convergence is the concept of, very generally, any kind of infinite process or any kind of extended process getting closer and closer to some limiting value. Okay? So some kind of process, I'm just being vague about what a process is, but some kind of process which goes on in time or extends out, gets closer and closer to some limiting value. So things converge, they get closer to some final state. Divergence is kind of when convergence doesn't happen. So a process is divergent if it is not converging to some fixed limiting value. Okay. This is a vague definition of those terms, not very precise or not being very clear about what exactly we're talking about. Just that idea of things getting closer and closer to some limiting state, that's convergence. Not doing that is divergence, the opposite. Now this is a big issue. It's a very key fundamental concept in, well, in lots of things, but in mathematics particularly. just send the signature sheet down. Has the signature sheet come down to you guys? No. So when you're finished with it, just send it back and down through the middle row. And why is it important? Why is convergence important? Well, whenever we apply mathematics to the real world, for instance, we build mathematical models of the real world to represent things in the world, any kind of engineering system or physical system like the climate or the weather system. We build a mathematical model, but of course, you know, it's only ever a very, very rough approximation to the truth, to how the thing is actually in the real world. You make lots of simplifying assumptions, and your model only incorporates certain facts or certain data from the real world. So models are always approximate, okay? So they never tell you the truth, really. They always just give you approximations to the truth. But that's not a crushing blow, or that's not so bad, because in principle we can always make our models, if you like, converge to the truth, or get closer and closer to the real situation by making them more detailed and taking in more data. So building models of the real world, you can make them better and better and better and make them converge to the truth in some cases. So here's an illustration of this. This is a graphic taken from, do I have the, oh, it's a bit bad. I don't have the reference to it there. This is taken from a report by the American Research Councils, the National Research Council in America. And I just want to focus you on the thing on the left. So these are four representations of kind of Europe, if you like, on the left. And these are illustrating the level of detail in the models that were in the IPCC. So the IPCC is the Intergovernmental Panel on Climate Change, a big international scientific body which is researching climate change and producing models and predictions of how the climate is going to develop in the future. The FAR is the first annual report, SAR the second annual report, third annual report, and they couldn't call the fourth one the fourth annual report because it's the same as the first annual report. So they had to call it annual report for it. Kind of silly. But you can see how as computing power became, as more and more computing power became available. Computers are getting faster all the time and cheaper all the time. So as the years go by, you get more and more computing power available, so that computer models of the climate were able to deal with a better and better approximation to the truth. I mean, the top picture, if I didn't tell you the top was Europe, you probably wouldn't recognize it as Europe. Just a load of blobs. And indeed, Britain and Ireland aren't even represented there. They don't even figure. These aren't exact pictures, they're just kind of rough suggestions. But by the time you get to the fourth annual report, you see the computer model is dealing with a fairly detailed model of the land masses in Europe. Okay? We can see Ireland, we can see Britain, we can see Iceland. We've got a fairly detailed look at the countries, and we can got fairly detailed elevation information, height information about mountains and so on. I think that's what I was told about. Okay. The stuff on the right is just indicating more and more aspects that were built into the model. So in the mid-1970s, they only considered rain, heat from the sun, and CO2. But by the fourth annual report, there's lots of other elements that are coming into the model. So the model is converging over time to the real situation, or the truth, whatever that is. At least in principle. So convergence and divergence is everywhere in applied mathematics. Okay? But moreover, even when you make your approximate model, you then set up a mathematical problem which you try and solve on that model. Try and predict what the temperature is going to be so many years hence, or the average temperature, predict what the sea level is going to be so many years hence. So you set up a mathematical problem within the model. Now it so happens, and you'll become more and more aware of this as you go through the course. Just get a book of notes there, guys. Thank you. Right. The mathematical problems you set up within those models can't be solved exactly. The equations, the differential equations that describe, say, the movement of, stick with the climate and weather, that describe the movement of heat through the atmosphere into the oceans, describe the movements of the atmosphere and oceans themselves. The nature of these equations is they can't be solved exactly. We can only find approximate solutions to them. Okay? But again, that's not such a bad situation, because the mathematical methods we have can, in principle, we can make those approximate solutions as close to the truth, in quotes, as we like, in principle. Okay, by refining the model or by investing more and more computing power into the solution. So even within it, the model is an approximation to reality, then the mathematical problem which is posed within the model can only be solved approximately. And our approximate solutions can be made to converge to the real situation. So we're making it a little bit more detailed now, and by the end of the lecture we'll be speaking very precisely about convergence. Just pick up a book of notes on your way in there on the back desk, thank you. But divergence is also everywhere as well. So to stick with the weather and climate example, see this bottom bullet point. When you build a model of the weather, say you're trying to predict the weather, you might make quite an accurate prediction for tomorrow. It's still a very good approximation for 3 or 4 days hence. But if you're trying to predict the weather, whether it's going to rain or what temperature it is, or what the wind speed is going to be for next week or the week after, the approximations, the accuracy of the predictions get worse and worse. Okay? So although your model of the weather can be churning away happily inside the computer and saying, oh, in 3 months' time the temperature is going to be this, wind speed that. Okay, the model is churning away, but the answers it's giving, in a sense, are diverging from the truth. But there's no guarantee that they're going to converge to the truth. Okay? Because whatever inaccuracies are there in the model, they get worse and worse and they expand as time goes on. When you're trying to predict the weather, the day-to-day weather into the future. So when you think about applied mathematics, when you look at it the right way, you can see this idea of convergence and divergence all over the place. But it's not just in applied mathematics. It's also important in pure mathematics as well. So if you're not, even if you're not interested in applications to the real world, you're just investigating numbers and mathematical structures for their own sake. Again, we see convergence and divergence as a key important idea. So, for instance, so this first bullet point. Some of this notation you might be too familiar with, but Saeed will develop some of this notation in the set theory lectures. So Z and Q, Z stands for the integers, from the German Zahlen for a number. The integers, Q stands for the rationals, it comes from the word quotient. So the integer numbers are, of course, all the counting numbers and their negative counterparts. And the rational numbers, Q, that's all the fractions you can form from integers, one integer divided by another. Okay, in some senses, those number systems are fairly straightforward to construct, to build them and to understand them mathematically, in a sense. But when you think of the number line, when you think of the fully detailed number line, the rationals don't capture all the numbers on the number line. The rationals don't capture every kind of possible length or quantity you can come up with, okay? Because things like the square root of 2, or pi, the ratio of the circumference to the diameter of a circle, e, the base of the natural logarithm, and so on. These are numbers, these are quantities that we can construct fairly rigorously, mathematically, but they aren't rational numbers. They're so-called irrational numbers. So the non-rational numbers, the irrational numbers, are quite subtle and tricky things to get a hold of, and quite tricky things to deal with rigorously and mathematically. So the question then is, how can you build them, or how can you deal with them using the more basic, easily understood topics of integers and rational numbers? Well, that is done using the concept of convergence. I'm just highlighting a few things here, just showing you a few examples. We'll be dealing with things much more methodically shortly. But for instance, this equation here is an equation for pi, or pi over 4. On the left-hand side. It claims that pi over 4 is equal to 1 minus a third, plus a fifth, minus a seventh, plus a ninth, minus 11th, and so on. I think I mentioned this in the introductory lecture, in the needle dropping session last week. No, but that's an infinite sum. See the sum on the sigma n equals 1 to infinity. This indicates that that sum goes on forever. Well, that's kind of a bit hard to understand. The sum's going on forever. We'll deal with that rigorously as we go through the unit. Don't worry. But an infinite sum, well, you can think of that as an infinite process. You're adding things onto the sum each time. Now, the things you're adding on or subtracting off, of course, are getting smaller, aren't they? A third, a fifth, a sixth, a ninth, a third, a fifth, a seventh, a ninth, an 11th, and so on. The bits you're adding on and taking off are getting progressively smaller. So the sum is changing less and less. So if you think about the developing value of that sum, it's getting less and less. And it's actually converging. In fact, if you looked at the summary sheet on the Buffon's needle experiment we did last week, I've actually got a graph of that towards the bottom here. So that graph there shows the evolution of that series. So the first blue dot is at, was not even on the page because it's not even on the graph. The graph only goes down to 2.5 or something. No, sorry. This is the series gives you a value for pi over 4. So what I'm showing you in the graph is the value of the sum multiplied by 4. So I'm illustrating how it converges to the value pi. So you think about taking that quarter on the left-hand side and multiplying it by the value of the sum on the right-hand side. Okay. So we have this infinite process where you're adding and subtracting things, and the things you're adding and subtracting are getting smaller and smaller. So the blue dots are tracking the value of the sum as you add more and more bits onto it. And you can see they're converging to the number pi. They're getting closer and closer to the number pi. So pi is the value indicated by the red dotted line there, 3.14 something, something, something. But you see, all the numbers in these series, all the numbers in the series are rational numbers. So they're all just built out of adding fractions together, adding or subtracting fractions together. So the numbers in the sum are these easily understood basic objects, fractions of integers. But using them, you can build towards or capture this much more slippy, subtle kind of number, pi. Okay? So what we say is that this infinite series converges to the value pi over 4. It's closer and closer to the value pi over 4. I'll just pause for any quick questions. Anybody got a clarification they want to ask about it or not? We will be dealing with these things very rigorously and very methodically as well. Any questions at the moment? Okay. So that was all just to try and persuade you that convergence and divergence is a key fundamental topic, whether you're thinking about applied mathematics or even pure mathematics. Okay, it's a very key idea. Okay, so with some of that motivation out of the way, let's make things a little bit more concrete. Start to make some definitions and build up the course. Okay, you'll notice that the Mathematics Fundamentals course, and indeed all the mathematics units, indeed your whole mathematics degree, it builds one thing on top of the other. Okay? So all the stuff you do in first year is a building block for all the stuff you do in second year, and so on. Okay? The natural way to think about it. So we begin in very firm ground and make very clear definitions at the start to begin. Okay? So this definition is from the notes. You'll see it on at the bottom of page 1 in the notes. So remember, a series, this kind of infinite sum, or this long sum, we tend to call a series, but before we get to series, we're going to deal with simpler types of things, or more basic types of objects called sequences. And what we mean mathematically by a sequence is pretty much what we understand it from the everyday, day-to-day meaning of it. A sequence of things is just one thing after the other. Yeah? A list of items. And that's what we mean by a sequence. So a sequence is a list of elements. Now, they're usually going to be numbers that we do. We're usually going to be talking about sequences of numbers. But there are many other sequences of interest. We can talk about sequences of functions, sequences of groups. Basically, any type of mathematical object, you can make a sequence out of it. A sequence of instances of that object. But we'll pretty much deal with sequences of numbers in this course, or in this term for the moment. And we tend, when we're speaking generally about a sequence, okay, so sometimes we'll be investigating particular sequences, but often we'll want to talk about the concept of a sequence, the idea of a sequence, and talk about that. So we use this kind of notation to refer to the sequence. So the first element we call x1, second element x2, and so on. x3, x4, x5, and it continues indefinitely. Well, it may or may not continue. So these are, we use a variable with a subscript to indicate the element in the sequence. So we can write x1, x2, x3, x4, dot, dot, dot. That would indicate you've got an extended sequence. Or there's a more compact notation, this curly bracket notation here. So when we write curly brackets and a sequence element in the middle, xn with the general subscript, for instance n, and then outside the bracket we have a subscript and superscript to indicate the starting and ending values of the sequence. That stands for that sequence as well. So curly brackets xn, it's telling you n begins at 1 and then goes on to infinity. So that represents the sequence x1, x2, x3, x4, and so on. Oftentimes we'll leave out these superscripts and subscripts. A lot of the time we'll be dealing with infinite sequences. So often we might just write curly bracket xn. If it's understood from the context, if it's clear from the discussion where we are that we're talking about an infinite sequence. And speaking about the indexes generally like that, where you use a symbol or a letter for the index, the n there, that allows you to write down formulas or to specify sequences using formulas. So let's look at some nice examples here. So a very basic sequence here would be this one. The sequence Zm, I'm using Z for the sequence element and n for the index. And this sequence is defined by a formula Zm equals m. It's a nice, straightforward formula. So that's telling you that the mth element, Zm, is just equal to the number n. So this is the sequence of positive integers. Z1 is 1, Z2 is 2, Z3 is 3. So that's the sequence of positive integers. Certainly an infinite sequence. Is it converging? Does that sequence get closer and closer to some limiting value? Good, see a few shaking heads. No, it just grows and grows and grows. The integers get bigger and bigger and bigger. It's not getting closer and closer to some limiting value. Unless you might want to say, oh, infinity is a limiting value. But I don't think we should say that at the moment. Infinity isn't an integer, certainly. It's certainly not a number like the other ones. So, does infinity even exist? That's an important question. I think mathematicians are still probably trying to answer that question. They're still probably trying to agree the most sensible answer to that question. Because you certainly don't see infinity in the real world. I don't think. I'm not sure. Maybe space is infinite, maybe it's not. Some people build models of a space which is infinite in extent, of a universe that is infinite in extent. But I think you can also build consistent models of the universe which is not infinite in extent, which kind of wraps around on itself in some way. It's certainly hard to find infinity in the real concrete world. So we're going to say that top sequence diverges. Okay, a more interesting sequence might be something like the Fibonacci sequence. The Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 13, and so on. Continues on. Okay, we're going to call that Fn. F for Fibonacci. N is the index here. Of course, when you're dealing with all this stuff, never get too attached to the individual letters. Always be prepared to see the objects represented using different letters. Because letters, after all, are just symbols. They don't have any inherent meaning for us. We just use them as labels. The actual numbers are the important thing here for us. So how do we give a formula for the Fibonacci sequence? Well, we have to do it a little bit differently than before. We have to supply the first two elements. So we declare that F1 is 1. We declare that F2 is also 1. And then we can give a formula for it. The formula says that Fm is Fm minus 1 plus Fm minus 2. So you see interesting stuff going on with the indexing here. this is saying that the nth element in the sequence, fm on the left of the equation there, is equal to the sum of the two previous ones. Okay, because the thing that's at position m minus 1, that's the one that came before fm, and fm minus 2, that's the one that came in the sequence before m minus 1. This kind of thing is called a recurrence relation. So a recurrence relation is a way to define a sequence of elements. You have to supply the actual values for some of the initial terms. Not always two, sometimes more, sometimes less. And then you have a rule which tells you how to continue the sequence. So once we supply the first two values, using the rule we can declare what the third value is, and then the fourth value, and then the fifth value. Okay. And this Fibonacci sequence is interesting. You might be aware of it. It's referred to a lot. It embodies a very kind of a natural pattern or a natural way that things can evolve, and it can be observed in the real world in lots of areas, in the structures of plants and in population models of breeding animals and so on. So it pops up a lot. Okay, here's another example. We can talk about the sequence 1357, a sequence of odd integers, odd positive integers. 1357. We can give a formula for that. We can call that sequence AN. Why not? And the formula for it would be AN is equal to 2n minus 1. So when n is equal to 1, okay, I probably should supply the starting value for the index here. Sometimes people would start the indexing at 0 also. If you wanted to capture the odd positive integers, you wanted the indexing, the value of the subscript n to start at 0, then you'd need the formula 2n plus 1. So that the first element, the 0th element, would be 1. Second element, the 1th element, and the index is 1, will give you 3. It's also very important in mathematics, in pure mathematics, is the sequence of prime numbers. Everybody knows about prime numbers. Numbers that cannot be written as a product in any way, product of integers, except for writing themselves as 5 is equal to 5 times 1. Okay, that's writing 5 as a product, but apart from that, there's no other way to write 5 as a product. The prime numbers are very interesting, very important. So they're 2, 3, 5, 7, 11, 13, and so on. Then what's the formula for the sequence? How do you define the nth prime number? Does anybody know? You can't, exactly. I'd be very surprised if anybody did say, here's the prime. Okay. What?
I wish I could get the prime number.
If you came up, if you could fill in the blanks there, those question marks, you'd be world famous instantly. But it's probably not going to happen. And that's no slur on you. I'm not saying you're not capable of throwing it up. It probably won't happen because mathematicians have already proved a number of results about the impossibility of supplying an answer to the right-hand side. There is certainly, I think it's been proved, I might have to double check, but there's certainly no simple formula that can go on the right-hand side involving additions and multiplications of n. There's no just simple arithmetical formula that you can put on the right-hand side that will spit out all the prime numbers. That has been proven. So if you want to answer this question about being able to say definitively what the nth prime number is, it's going to have to be something a bit more sophisticated than a simple arithmetical formula with additions and multiplications. But yeah, I'll set that as homework to solve that. So we can talk about the sequence of prime numbers, certainly an interesting sequence to talk about. We study that in the second year course on number theory and cryptography, but we certainly can't supply a formula for it in the same way that we can supply a formula for the odd integers or the Fibonacci sequence and so on. Okay, how are we doing? Any questions at that point? That's kind of just setting up the notation, just making it clear the notation we're going to use. Now, okay, arithmetic and geometric series. Again, this is probably familiar to most of you. You would have encountered these terms before. But these are two So they're not specific sequences, they're types of sequences. Yeah? They're very well behaved, easy to understand sequences. An arithmetic sequence is one which each element in the sequence is just a fixed shift from the previous one. And that fixed shift amount doesn't change. It stays the same for the whole sequence. So an arithmetic sequence appears like this. It's got some initial value, A. The next value will be A plus D, where D is the shift amount. And you keep on adding D to continue the sequence. That's called an arithmetic sequence. You can give a formula for it. AN, and the indexing here will start at 1. AN is equal to A plus n minus 1 times D. Okay, that's our arithmetic sequence. I think if we don't write down any indexing, we'll always, by convention, we'll take the indexing to begin at 1. We've also got things called geometric sequences. They behave very regularly as well, except it's not through adding a fixed shift amount. This time it's by by expanding, by scaling the term of the sequence by a fixed amount. Okay? So the first term in the sequence is A, some value A. The second term is going to be A multiplied by R. So you scale the value of A by multiplying it by a quantity R. Then to get the third term, you multiply by R again. It goes to AR squared. To get the fourth term, you multiply by R again, AR cubed. So that can be given a formula, A times R to the n minus 1. That's the formula for AN, nth term of a geometric sequence. So both of these types of sequence, you can call them their two-parameter sequences. It takes two parameters to specify an arithmetic sequence. The initial value A and the fixed shift D. And again, to specify a geometric sequence, it takes two parameters, some fixed value A, initial value A, and some fixed scaling factor R. Here's a good question. When does an arithmetic sequence converge? Typically, do arithmetic sequences converge? Typically. No, why not?
Because the number just keeps getting bigger.
Big, yeah, the number keeps moving. It keeps shifting by a fixed amount all the time. Yep. Keeps getting bigger, or bigger in the negative direction, perhaps, if D is a negative quantity. So it's certainly not getting closer and closer to some limiting value. So there's one special case. Well, not just one. There's an infinite amount of convergent arithmetic sequences. They're pretty boring sequences. Somebody's got to. If you got the answer, shout it out. You'll kick yourselves when you hear it.
Yeah, 0.
Adding 0 when the parameter D is 0. Very good. Pretty boring sequences. Those are constant sequences. You're just repeating the same number. A. It is convergent. It's getting closer and closer to some final limiting state. Just A itself. It's a pretty boring sequence, but it is convergent. So, much quicker. What are the convergent geometric series? Good. When R is between, so explain why is that convergent? What's a convergent?
What's it convergent to?
Yeah. Anybody else? When R is between 1 and -1, what's the geometric sequence convergent to? You should know it. Why should you know it? 0. It's the same answer you gave a minute ago. 0. When the scaling factor is between 1 and -1, you're making things smaller in absolute value. When you multiply something by something strictly between 1 and -1, it gets closer to 0. When you keep doing that, it gets closer and closer to 0 still. And it gets smaller and smaller, and there's no limit to how small or how close to 0 it can get. That's good. So when r is strictly bigger than 1, yeah, the geometric sequence is divergent, of course. Except in one special case. Again, it's pretty boring. The special case where the parameter a is 0. Then you can multiply 0 by whatever r you want. It's never going to get any bigger. It's always going to be 0, 0, 0, 0, 0, 0. Again, a trivially convergent sequence. So those constant sequences, the constant arithmetic sequence, you'd call that trivially convergent. It's not interesting convergence because it's just stuck at the same value. But when r is less than 1, absolute value less than 1 in a geometric sequence, that is an interesting type of convergence because the sequence is changing in value and it's getting closer and closer to 0. Now we'll talk about this in a much more precise way pretty soon, in the second lecture, I think, second or third lecture. So far we've just been talking about convergence as getting closer and closer to something. And that's a little bit hand-waving. You can ask exactly what do you mean by that. Because some things will get closer and closer to a limiting value very fast. Some things will take a long time or do so very slowly. So we haven't got a very precise handle, a very technical handle on what convergence is yet. We'll be encountering that shortly. How are we doing? 9:44. I think I might bring it to a close gradually now. We'll continue with this on the Thursday lecture. We'll get a bit more active on the Thursday lecture. We'll start to do some problems on the paper and so on. But don't jump out of your seats yet. I just want to